Definition of machine learning. To understand machine learning, ML, let's conceptualize its essence through Python code. This will not be an actual program, but a metaphorical representation to convey the idea of how machine learning works at a foundational level. In this metaphorical code, machine learning is depicted as a process wherein a machine, represented as the machine learning class, learns from data. The learn from data method takes data as input and returns knowledge, which is a transformation of raw data into an abstract understanding or patterns, extract patterns function. The process is akin to how ML algorithms analyze and learn from data to make decisions or predictions. This code snippet abstractly illuminates the essence of machine learning, taking data, discovering patterns, and turning these into actionable insights. Types of machine learning: supervised, unsupervised, and reinforcement learning. Understanding the types of machine learning is critical for choosing the right algorithm for your data problem. Supervised learning involves learning a function that maps an input to an output based on example input-output pairs. Unsupervised learning, on the other hand, deals with learning patterns from untagged data. Reinforcement learning is about taking suitable actions to maximize reward in a particular situation. In the code provided, we first import necessary modules from scikit-learn, a popular machine learning library in Python. For supervised learning, we've given an example of using logistic regression to classify the iris dataset after splitting it into training and testing sets. This demonstrates learning from labeled data. For unsupervised learning, we used k-means clustering to group iris dataset samples without any labels, showcasing how patterns can be discovered in data without explicit guidance. Lastly, while a reinforcement learning example isn't directly shown due to its intricate nature involving environments and agents, it's crucial to understand that it focuses on learning strategies to make sequences of decisions by receiving feedback in form of rewards. Applications of machine learning. Machine learning is a fundamental branch of artificial intelligence that has a wide range of applications in today's world. It enables computers to learn from data and improve their performance over time without being explicitly programmed for each task. Here, we'll explore a simple example that demonstrates how ML can be used in one of its applications: predictive modeling. In this code, we showcase a predictive modeling application of machine learning using the iris dataset. We start by loading the iris dataset, which includes features of iris flowers and their corresponding species. The dataset is divided into a training set and a test set, allowing the model to learn from the training data and then be evaluated on unseen data. A random forest classifier, a type of ensemble learning algorithm, is used to create the model. It is trained with the training data and then used to make predictions on the test set. This example underscores how machine learning can be applied to classify or predict the category of new observations based on historical data. Machine learning versus traditional programming. In traditional programming, developers write explicit rules in code for tasks. With machine learning, the system learns from data to create its own rules. In traditional programming, if we wanted to classify emails into spam or not spam, we might write specific rules based on words commonly found in spam. We'd have code like if winning in email and prize in email classify as spam. Conversely, in a machine learning approach, we feed a system thousands of example emails labeled as spam or not spam. The system then learns patterns that determine the classification without explicit rules written by us. This allows it to adapt to new unseen spam emails better than static rule-based systems. Python syntax basics. Understanding the basics of Python syntax is essential for machine learning projects. Python is known for its readability and simplicity, allowing developers to write clear code for complex algorithms. Let's start with a very simple example, printing a text to the screen. In this piece of code, the print function is used to output the string "Hello, machine learning" to the console. Strings in Python are enclosed in either single quotes or double quotes. This is a basic example of Python syntax, showcasing how to execute a simple command. The print function is often used to display results or debug by showing variable values. NumPy for numerical computing. NumPy is a fundamental package for scientific computing in Python, providing support for arrays, matrices, and high-level mathematical functions to operate on these data structures. It is crucial for performing efficient numerical computations in Python and serves as the backbone for many other scientific libraries. Let's start with creating a NumPy array. In this code snippet, we first import the NumPy library using the alias np for convenience. Then, we create a one-dimensional array, A, using the np.array function and passing a Python list 1, 2, 3 as the argument. Finally, we print the array. This demonstrates the basic method of array creation in NumPy, which is foundational for numerical computing tasks. Pandas for data manipulation. Pandas is a powerful Python library for data analysis and manipulation. It offers data structures and operations for manipulating numerical tables and time series. Learning to manipulate data with pandas is crucial for machine learning, as data pre-processing, exploration, and analysis are essential steps in the machine learning pipeline. In this section, we'll start with the basics of creating, reading, and writing data with pandas. In this code, we first import the pandas library as PD for ease of use. Then we create a dictionary named data with 3 keys: name, age, and city, each corresponding to a list of values. These keys become the column headers, and the lists are the column values when we create a data frame. A data frame is a 2-dimensional labeled data structure with columns of potentially different types, similar to a spreadsheet. The pd.dataframe data command creates a data frame from the dictionary. Finally, we use print.df to display the data frame. This operation is fundamental in pandas for creating data structures for further manipulation and analysis. Matplotlib and Seaborn for data visualization. Matplotlib is a plotting library for the Python programming language and its numerical mathematics extension, NumPy. Seaborn is a Python visualization library based on Matplotlib that provides a high-level interface for drawing attractive and informative statistical graphics. In the code, we first import the matplotlib.pyplot under the alias plt and Seaborn under the alias sns. We then define a simple list named data to serve as our dataset. Using Matplotlib, we create a basic line plot by calling the plot function and passing our data. We set the title of the plot using pl.title and finally display it using plt.show. Similarly, for Seaborn, we set the style to dark grid for a better background using snsset. We then use sns.lineplot to create a line plot. Seaborn automatically infers the x and y values from the past dataset. Lastly, we title our plot and display it with plt.show. This illustrates the basic usage of both libraries for creating simple line plots. SciPy for scientific computing. SciPy is a Python library used for scientific computing and technical computing. It builds on NumPy and provides a large number of functions that operate on NumPy arrays and are useful for different types of scientific and engineering applications. For machine learning, it's often used in tasks involving linear algebra, optimization, integration, and statistics. Here's a simple example of using SciPy to perform an interpolation, which is a method of constructing new data points within the range of a discrete set of known data points. The code first imports interp1d from scipy.interpolate and NumPy. It simulates known data points by using np.linspace to generate 10 linearly spaced numbers between 0 and 10, and calculates their sign values to simulate a function. An interpolator object is created from these known points using interp1d, which assumes linear interpolation by default. Then, the interpolator is used to interpolate, the value at a new point, x equals 5.5. Interpolation is useful in machine learning when we have missing data or want to make predictions at points where we don't have data. Linear algebra. Linear algebra is a branch of mathematics that deals with vectors, vector spaces, also called linear spaces, linear transformations, and systems of linear equations. It provides a way to describe and perform operations on data in a concise manner. In machine learning, linear algebra is fundamental in the representation and manipulation of data and algorithms. In the provided code snippet, we first import NumPy, a powerful library for numerical computations. Two vectors, vector A and vector B, are defined using NumPy arrays. Vector addition is performed simply by using the plus operator resulting in a new vector C that represents the element-wise addition of the two vectors. The dot product of vector A and vector B is calculated using np ... which multiplies corresponding elements of the two vectors and sums the results, providing a measure of the vector's similarity. Calculus. Calculus, particularly differentiation and integration, plays a crucial role in machine learning. Differentiation helps in finding the rate at which a function is changing at any point, which is fundamental in optimization problems such as gradient descent. Let's explore this concept by finding the derivative of a simple function. The code defines a simple quadratic function, fx equals x squared, and its derivative f per x equals 2x, using lambda functions. It then uses NumPy to generate an array of x values, and matplotlib to plot both the function and its derivative. The plot visually demonstrates how the derivative represents the slope of the original function at any point. This visualization is a fundamental concept in calculus, highlighting the relationship between a function and its rate of change, which is pivotal in understanding how gradient descent optimizes functions in machine learning, probability, and statistics. In machine learning, understanding the basics of probability and statistics is crucial as it forms the foundation for many algorithms. Probabilities help us measure the likelihood of events, while statistics allow us to analyze and interpret data. Let's explore some basic operations using Python. In the code, we're using Python's NumPy library to generate a sample set of data, representative of a real-world dataset. This sample data is generated using np.random.randen, which creates a dataset with 1,000 values, following a standard normal distribution. We then compute two fundamental statistical measures, mean and variance, using np_mean_data and np.var_data, respectively. The mean provides us with the average value, indicating the central tendency of the data. Variance gives us an idea of how much the data is spread out or dispersed around the mean. These measures form the basics of understanding any dataset in machine learning. Optimization techniques. Optimization techniques are fundamental to machine learning. They aim to adjust a model's parameters to minimize or maximize some function, typically a cost or loss function when minimizing, or an accuracy or performance function when maximizing. Gradient descent is one of the most common optimization algorithms. This code defines a simple gradient descent algorithm. Parameters are gradient, function computing the gradient, start, initial point, learn rate, learning rate, and n iterations, maximum iterations, tolerance, stop if improvement is below this. It iteratively updates the vector by moving in the negative direction of the gradient to minimize the function, scaled by learn rate. It stops if the change is less than tolerance to prevent unnecessary computation after converging sufficiently close to a minimum. Handling missing data. Handling missing data is crucial in machine learning to maintain the quality of the dataset. Missing values can significantly impact the model's accuracy. Imputation is a common technique where missing values are replaced with statistical measures like mean, median, or mode. Let's assume we are working with a pandas data frame df and want to fill missing values in the age column with its mean value. This code snippet first imports the pandas library and creates a data frame df with two columns, age and name. There's a missing value in the age column represented by none. The fillNow method is then used on the age column, where df_age.mean calculates the mean of non-null values in the age column and fills the missing value with this mean. The inPlace equals true argument modifies the original data frame directly. After this operation, all missing values in age are replaced with the mean age, ensuring the column has no missing values. Data cleaning. Data cleaning is an essential step in data pre-processing, ensuring the quality and accuracy of data before it is used in machine learning models. It involves handling missing values, inconsistent data, and outliers to improve data quality. Below is a simple example using Python's pandas library to fill missing values in a dataset. In this code, we first import the pandas library, which is crucial for data manipulation in Python. Then, we create a data frame df with some missing values represented by none. Using the fillNow method with the method parameter set to fill, forward fill, we fill missing values with the last observed non-null value in the column. The in-place equals true argument modifies the original data frame instead of creating a new one. This approach is simple but effective for certain datasets, where the assumption that the next value might be similar to the last known value is reasonable. Feature scaling, normalization and standardization. In machine learning data preprocessing, feature scaling is crucial for algorithms that compute distances between data points. It includes normalization and standardization. Normalization scales the data between 0 and 1. Standardization shifts the distribution of each feature to have a mean of 0 and a standard deviation of 1. The code snippet shows how to apply normalization and standardization using scikit-learn on a dataset data. For normalization, min-max scaler scales features to a given range, here between 0 and 1, ideal for algorithms sensitive to input values scale. Fit transform data computes and applies the transformation. For standardization, standard scaler removes the mean and scales each feature variable to unit variance. This is important for models like KNN or gradient descent, ensuring that all features contribute equally to the result. Encoding categorical data. Categorical data are variables that contain label values rather than numeric values. The number of possible values is often limited to a fixed set. Categorical data must be converted to numbers so that they can be included in machine learning algorithms. We'll cover two common methods for encoding categorical data: label encoding and one-hot encoding. Label encoding converts each class under specified feature to a unique integer. This is particularly useful for ordinal data, i.e., when categories have a clear ordering. However, machine learning models might interpret the numerical values as having some sort of hierarchy or order, which might not be desired for nominal data. One-hot encoding, on the other hand, converts each category value into a new categorical column and assigns a 1 or 0, true-false. Each integer value is represented as a binary vector. This is very useful for nominal data, where no ordinal relationship exists. One-hot encoding can significantly increase the dataset's dimensionality if there are many unique categories. Train test split. In machine learning, it's crucial to evaluate the performance of a model on data it hasn't seen during training. The train test split is a technique to divide the dataset into two parts, one for training the model and the other for testing its performance. This helps in assessing how well the model generalizes to new unseen data. In this code snippet, train test split from sklearn.model selection is used to split arrays or matrices into random train and test subsets. X represents the input features and Y the target variable. The test size equals 0.2 parameter indicates that 20% of the data is reserved for the test set, while the remaining 80% is used for training. The random state equal 42 ensures that the split is reproducible. Different runs will produce the same results. Linear regression. Linear regression is a foundational algorithm in machine learning, aimed at predicting a continuous outcome variable Y, based on one or more predictor variables, X. It assumes a linear relationship between these variables, formulated as y equals mx plus b, where m is the slope and b is the intercept. This code snippet demonstrates the basics of using scikit-learn's linear regression model. It starts by importing the linear regression class from sklearn.linearModel. Then it creates a simple dataset where x is the feature matrix and y is the target variable, both aligned to ensure a direct linear relationship. Model equals linear regression creates a linear regression model instance. Model.fitxy fits the model to our dataset, finding the optimal linear relationship between x and y. Finally, model.cof0 and model.intercept retrieve the slope m and intercept b of the fitted line, essentially revealing the derived equation y equals mx plus b for prediction. Logistic regression. Logistic regression is a classification algorithm used when the output is categorical. It estimates probabilities using a logistic function, which is S-shaped and maps any real-valued number into a value between 0 and 1, making it useful for estimating probabilities. Let's see a simple implementation using Python's scikit-learn library on a binary classification problem. In this code snippet, we start by importing necessary modules. We use load_iris to fetch a dataset, and train test split to divide it into training and testing sets. Then, we create an instance of logistic regression and fit this model to our training data using the fit method, Once the model is trained, we use predict to generate predictions on our testing set. Finally, predictions are printed out, showing which class each test sample is predicted to belong to. Throughout this process, the logistic regression model attempts to find the best parameters, weights, that map input features to the target variable's probability, leveraging the logistic function for the transformation. K-nearest neighbors, KNN. K-nearest neighbors, KNN, is a straightforward, instance-based learning algorithm where the class of a sample is determined by the majority class among its K-nearest neighbors. It's highly versatile, applicable for classification and regression. KNN makes predictions just in time by calculating the similarity between an input sample and each training instance. This Python code demonstrates a basic usage of the K-nearest neighbors algorithm with the scikit-learn library. First, we import the K-neighbors classifier from sklearn.neighbors. We then instantiate the classifier, specifying n neighbors equals 3, which means the algorithm considers the 3 closest points, neighbors, to make a prediction. Fit method is used to train the model on training data, xtrain, ytrain. Finally, we use the predict method on the xtest to get predictions. The choice of k impacts the algorithm's performance and requires tuning. Support vector machines, SVM. Support vector machines, SVM, are a set of supervised learning methods used for classification, regression, and outliers detection. The main idea behind SVM is to find the hyperplane that best separates different classes in the feature space. SVM tries to maximize the margin between the closest points of the classes, which are known as support vectors. In this code snippet, we first import the SVC, support vector classifier, from the sklearn.svm module. We then prepare a hypothetical feature set class to represent our data, which consists of points, features, and labels, classifications. We use SVC with a linear kernel, a common choice for binary classification problems. The clf.fit method is called with our features and labels, training the model to find the optimal hyperplane that separates the classes. This process involves selecting the support vectors that determine the margin. By maximizing this margin, SVM improves its classification accuracy. Decision trees and random forests. Decision trees are a type of supervised learning algorithm used for both classification and regression tasks. They split the data into subsets using decision rules derived from the features, aiming to increase the homogeneity of resultant subsets regarding the target variable. In this code example, we import decision tree classifier from sklearn.tree, which is a module used for creating decision tree models in Python. We provide a small dataset X with corresponding labels Y and create an instance of the classifier. After fitting our model to the data via the .fit method, we predict the label of a new observation to 2. The prediction process involves traversing the tree, created during training, according to the values of the input features, until reaching a leaf node. Ensemble learning methods. Ensemble learning methods combine multiple machine learning models to improve the overall performance. The primary principle is that a group of weak learners can come together to form a strong learner. We'll illustrate this concept using a simple implementation of random forest, a popular ensemble method. In the provided code, we utilize scikit-learn to create a synthetic dataset with make classification, tailored for classification tasks. This dataset consists of 1,000 samples with 4 features, of which 2 are informative for the classification process. A random forest classifier is then instantiated with 100 trees, n estimators equals 100, and a maximum depth of 2 for each tree to limit overfitting. We train fit, this classifier, with our dataset. Finally, feature importances is printed to showcase the relative importance of each feature according to the model. This illustrates not just ensemble learning via random forests, but also provides insight into feature relevance in prediction. K-means clustering. K-means clustering is a popular unsupervised learning algorithm that partitions a dataset into K distinct clusters based on feature similarity. The goal is to minimize the variance within each cluster. The process involves randomly selecting K points as cluster centers, assigning each data point to the nearest center, and then updating the centers based on the means of the assigned points. This process repeats until the assignment of points to clusters no longer changes significantly. In this Python code, we use the sklearn.cluster module to implement k-means clustering. We start by importing the necessary libraries. np.array creates a dataset X with 6 points. The k-means class is initialized with 2 clusters and a random state for reproducibility. By calling fit on X, the algorithm calculates the clusters. The labels property shows the assigned cluster of each point, indicating which of the 2 clusters, 0 or 1, each point belongs to. The cluster centers property reveals the coordinates of the center of each cluster, demonstrating how the algorithm finds the optimal positions to minimize variance within each cluster. Hierarchical clustering. Hierarchical clustering is a method of cluster analysis which seeks to build a hierarchy of clusters. Strategies for hierarchical clustering generally fall into 2 types: agglomerative, bottom-up, where each observation starts in its own cluster, and pairs of clusters are merged as one moves up the hierarchy, and divisive, top-down, where all observations start in one cluster, and splits are performed recursively as one moves down the hierarchy. This example demonstrates a simple implementation of agglomerative hierarchical clustering using the SciPy library. Initially, we import necessary modules. The linkage function is used to compute the linkage matrix, where ward is the linkage method specifying the distance metric for clusters, aiming to minimize the variance within each cluster. The dendrogram function from SciPy generates a dendrogram visualization representing the hierarchical relationship between clusters. X consists of sample data points in a 2-dimensional space. The dendrogram plots these points in clusters based on their distance, with the y-axis representing the hierarchical levels of agglomeration. This visual representation aids in understanding the structure of data and deciding on the number of clusters by cutting the dendrogram at a specific level. Principal Component Analysis, PCA. Principal Component Analysis, PCA, is a technique used to emphasize variation and bring out strong patterns in a dataset. It's especially useful in reducing the dimensionality of data by transforming it into a new set of variables, the principal components, which are orthogonal, uncorrelated, ensuring the first principal component has the highest variance. In this code snippet, we begin by importing PCA from Sklearn's decomposition module and NumPy for array manipulation. The dataset X is a simple array for demonstration purposes. We initialize a PCA object with n components equal 1, indicating we want to reduce the data to a single principal component. By using fit transform on X, PCA learns the transformation and applies it, resulting in comp, the dataset transformed into a single dimension. This process is particularly useful for data visualization, noise filtering, or as a pre-processing step for further analysis. Anomaly detection. Anomaly detection is a technique used in machine learning to identify unusual patterns or observations, which differ significantly from the majority of the data. These anomalies can indicate critical incidents, such as fraud, network intrusions, or system failures. One common approach for anomaly detection is using the isolation forest algorithm, especially when dealing with multidimensional data. In the provided code, we first import the necessary isolation forest model from sklearn.ensemble and NumPy for numerical operations. We define a simple dataset X containing several 2-dimensional points. Then, an isolation forest model is instantiated and fitted with our data using clf.fitX. After the model has learned from the data, it predicts whether each data point is an anomaly or normal by calling clf.predicts. The predictions are marked with -1 for anomalies and 1 for normal data points. This method is efficient for identifying outliers in a dataset without needing a labeled dataset for training. Association rule learning. Association rule learning is a rule-based machine learning method used to find interesting associations or relationships between data items within large datasets. It's widely used in market basket analysis, where it helps uncover the relationships between products purchased together. The core idea is to find rules that determine how the occurrence of an item affects the occurrence of another item within a transaction. This concept is encapsulated by metrics like support, confidence, and lift. This code demonstrates how to use the MLXtend library for performing association rule learning on a small dataset. Initially, a dataset of transactions is created, where each transaction is a list of items. The transaction encoder is used to convert these transactions into a binary matrix, a step necessary for the a priori algorithm, which searches for frequent item sets based on a minimum support value. Here, a priori function is applied with min support or 0.5 to find item sets frequently bought together in at least 50% of transactions. Finally, association rules function is employed to extract rules that have a minimum confidence level of 70%, indicating that the rules are at least 70% reliable. Introduction to neural networks. A neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. Neural networks reflect the behavior of the human brain, allowing computer programs to recognize patterns and solve common problems in the fields of AI, machine learning, and deep learning. In the provided code snippet, we define a simple neural network with a single neuron. Firstly, we import NumPy, a fundamental package for scientific computing with Python. We define the sigmoid function, which is a common activation function in neural networks, used to introduce nonlinearity. The inputs array represents the input features to the network, while the weights are the parameters the network will learn to make accurate predictions. The bias is like an intercept in linear regression, added to the input's weighted sum. Using the dot product of inputs and weights, plus the bias, we calculate the neuron's raw output. Finally, we pass this raw output through the sigmoid function to get the neuron's activated output. This output can be viewed as the probability of the input belonging to a certain class in simple classification tasks. Activation functions. Activation functions help neural networks make complex decisions. They decide whether a neuron should activate or not, introducing nonlinearity into the model, which allows the network to handle more complex data. Common activation functions include sigmoid, tand, RealU, and softmax. This code demonstrates how to implement two popular activation functions, sigmoid and RealU, using Python and NumPy. The sigmoid function squashes the input values between 0 and 1, making it useful for binary classification tasks. RealU, rectified linear unit, activates a neuron only if the input is positive, improving the network's training speed and performance. The example usage shows how these functions behave with an input value of 2. Backpropagation and gradient descent. To optimize a neural network, we need a way to adjust our weights in response to the error our network outputs. Backpropagation efficiently computes the gradient of the loss function with respect to each weight by the chain rule, allowing us to update the weights in the right direction. Gradient descent then uses this information to minimize the loss by adjusting the weights in small steps towards the gradient's negative direction. In this code, update weights function takes the current weights of the network, the gradient of the loss function with respect to those weights, computed via backpropagation, and a learning rate that determines the size of the steps we take towards minimizing the loss. It updates each weight by subtracting a fraction, determined by learning rate, of its gradient from itself. This step is fundamental in gradient descent, guiding the network to gradually reduce error through training iterations. Convolutional neural networks, CNNs. Convolutional neural networks, CNNs, are a class of deep neural networks, most commonly applied to analyzing visual imagery. They are especially powerful for tasks like image recognition, classification, and detection. A CNN automatically detects the important features without any human supervision. Their architecture is inspired by the natural visual perception mechanism of the living creatures. This code outlines the basic structure of a convolutional neural network, CNN, using Keras. It starts with importing necessary modules, followed by creating a sequential model. The model begins with a convolutional layer, conv2D, with 32 filters of size 3x3 and RealU activation, processing images of shape 664x3, height, width, color channels. It includes a max pooling layer to reduce spatial dimensions, downsampling. The flatten layer converts the 2D matrix data to a vector, allowing it to connect to a dense, fully connected layer. Lastly, it adds a final dense layer with a sigmoid activation function for binary classification. The model is compiled with the Adam optimizer and binary cross-entropy loss function, tracking the accuracy metric. Recurrent neural networks. RNNs. Recurrent neural networks, RNNs, are a class of neural networks designed for processing sequential data, where the order of data points is crucial. Unlike traditional feed-forward neural networks, RNNs have connections that form directed cycles, allowing information to persist. In the provided code, we're utilizing PyTorch to define and use an RNN layer. nn.rnn creates a recurrent layer with specified input and hidden layer sizes. Input size equals 10 defines each input vector's dimension, and hidden size equals 20 specifies the size of the hidden layer. With num layers 2, our RNN consists of 2 layers, enhancing its ability to capture complex patterns. By setting batch first equals true, the input tensor's first dimension is treated as the batch size, aligning with X's dimensionality. X simulates a batch of input sequences, where we have 3 sequences, each 5 steps long with 10 features. Upon executing the forward pass, RNN layer X, we obtain the output for each time step and the last hidden state. Long short-term memory networks, LSTMs. Long short-term memory networks, LSTMs, are a type of recurrent neural network, RNN architecture, used in deep learning. They are designed to overcome the vanishing gradient problem that affects standard RNNs. LSTMs are particularly useful for learning from sequences of data like text, time series, or audio. They can remember information for long periods, which makes them superior for tasks requiring understanding context over time. In this example, we're using Keras to build a simple LSTM model for a sequence prediction problem. Initially, we import necessary modules. Sequential allows us to create a linear stack of layers in our model. LSTM and dense are types of layers we're adding to our model. In model.add LSTM50, return C true, input shape equals time steps n features. 50 represents the number of LSTM units. Return sequences is set to true because we're adding another LSTM layer after. The second LSTM layer has 50 units but doesn't return sequences, making it suitable for connecting to a dense output layer. Dense 1 signifies an output layer with a single unit. Finally, we compile the model using the Adam optimizer and mean squared error loss function, fitting for regression tasks. Generative adversarial networks, GANs. Generative adversarial networks, or GANs, consist of 2 models, a generator and a discriminator. The generator learns to generate data similar to a certain distribution, e.g., real images, while the discriminator aims to distinguish between real and generated data. Both models are trained simultaneously in a game-theoretic approach, where the generator tries to maximize the error of the discriminator, and the discriminator tries to minimize its error. The provided code is a basic template for defining the 2 main components of a GAN in PyTorch, the generator and the discriminator. Both classes inherit from nn.module, making them PyTorch models. Inside each class, you'd normally define the layers and the forward pass, which dictates how the data flows through the model. The generator typically includes layers that upsample the input noise to generate data, e.g., images, while the discriminator includes layers that downsample the input data to classify it as real or fake. Initializing these models, G for generator and D for discriminator, is the first step towards implementing a GAN. Introduction to reinforcement learning. Reinforcement learning, RL, is a type of machine learning where an agent learns to make decisions by taking actions in an environment to achieve some goals. The agent receives rewards by performing correctly and penalties for wrong actions, guiding it to learn the best strategy or policy. Below, we model a simple RL scenario using Python. This code snippet illustrates a basic reinforcement learning concept without using any RL-specific library. An agent, in this case, simply a counter for position, makes a decision based on its current state, position. If the position is less than 10, it moves right by increasing its position, imitating an action, receiving a reward of 1 for moving in the preferred direction. Once it reaches or exceeds the position of 10, it receives no further rewards, simulating a simple goal achievement. This basic example mimics how decisions are made in reinforcement learning, taking actions in response to the environment's state to maximize some notion of cumulative reward. Markov decision processes. Markov decision processes, MDPs, provide a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision maker. MDPs are useful for studying optimization problems solved via dynamic programming and reinforcement learning. An MDP is defined by a set of states, actions, transition probabilities, and rewards. Let's consider a simplified MDP example using Python. In the provided code snippet, we define a simple MDP model with 3 states: sleep, ice cream, and homework, and 2 possible actions: study and play. The transition probabilities dictionary stores the probabilities of moving from one state to another given a particular action. These probabilities must sum to 1 for each action state pair. The rewards dictionary contains the rewards received for performing an action in a specific state. This setup helps in visualizing how actions taken in different states lead to different probabilities of moving to other states and receiving certain rewards, laying the foundation for understanding more complex MDPs and their solution methods. Q-learning. Q-learning is an off-policy reinforcement learning algorithm that seeks to find the best action to take given the current state. It's aimed at teaching the agent how to act optimally by learning the Q values, which are estimates of the rewards for taking action in a given state. Here, we'll implement a basic Q-learning algorithm. This piece of code demonstrates the implementation of Q-learning on a simple reinforcement learning environment. We start by initializing a Q table with zeros, representing the Q values for all state action pairs. The Q table helps the agent to choose actions over time. In the loop for each episode, we reset the environment and retrieve the initial state. Within the loop, we select actions using a policy derived from the Q table, max Q value for the current state, perform the action, and receive the next state and reward from the environment. Then, the Q value is updated using the formula, incorporating the learning rate, reward, and discount factor. This process repeats until the environment signals that the episode is done, e.g., the goal is reached or a maximum number of steps is exceeded. Policy gradients. Policy gradients are a class of algorithms in reinforcement learning that operate by directly optimizing the policy that the agent follows. Unlike value-based methods that aim to predict rewards, policy gradients look to adjust the agent's actions in a way that maximizes the expected rewards over time. A common approach to implement policy gradients is through the use of neural networks, where the network's predictions guide the agent's actions. The code outlines a simple implementation of a policy gradient method using TensorFlow. We start by defining placeholders for the actions taken by the policy, the advantages, which tell us how good an action is relative to others, and the predicted probabilities for each action. The predicted probs placeholder contains the output from the policy network, indicating the probability of taking each possible action. We then use these probabilities to compute the loss, which is minimized when the probability of taking good actions, ones that lead to higher rewards, is maximized. This is achieved by multiplying the log probabilities of the taken actions, act probs, by the advantages and taking the negative mean. Finally, an optimization step updates the policy to maximize expected rewards. This process iterates with the policy gradually learning to favor actions that lead to better outcomes. Deep reinforcement learning. Deep reinforcement learning combines neural networks with a reinforcement learning architecture that enables software agents to learn the best actions possible in virtual environments to achieve their goals. The Q-learning algorithm is one of the fundamental approaches in deep reinforcement learning. This code snippet demonstrates the fundamental Q-learning update equation applied in deep reinforcement learning. The Q table, initialized randomly, represents the expected rewards for actions taken in different states. Alpha is the learning rate, determining the weight of new information. Gamma is the discount factor, influencing the importance of future rewards. By simulating a scenario where an agent in state 1 takes action 0 and moves to state 3 with a reward, the Q table is updated using the Q-learning formula. The formula adjusts the Q value for the current state action pair towards the reward received, plus the discounted maximum future reward, thereby learning the optimal policy. Cross-validation. Cross-validation is a statistical method used to estimate the skill of machine learning models. It is commonly used to compare and select a model for a given predictive modeling problem because it is easy to understand, easy to implement, and results in skill estimates that generally have a lower bias than other methods. The most common form of cross-validation is k-fold cross-validation. In this code snippet, we first import the necessary functions and classes. We use make classification to generate a synthetic dataset with 1,000 samples, where each sample has 20 features, and there are 2 classes. We then instantiate a random forest classifier with 10 trees. The cross-val score function is used to perform 5-fold cross-validation on the classifier using our dataset. It essentially splits the data into 5 subsets, trains the model on 4 of them, and tests it on the 5th, repeating this process 5 times, each time with a different subset as the test set. The result is an array of scores representing the accuracy of our model on each fold. Performance metrics: accuracy, precision, recall, F1 score. Evaluating a model's performance is crucial for understanding its effectiveness in making predictions. Metrics such as accuracy, precision, recall, and F1 score provide different insights. Accuracy measures the overall correctness of the model. Precision measures the model's ability to return only relevant instances, while recall assesses how many actual positives the model correctly identified. F1 score provides a balance between precision and recall. Here's how to calculate these metrics using Python and scikit-learn. This code snippet shows how to calculate accuracy, precision, recall, and the F1 score using scikit-learn for a given set of true labels, y_true, and predicted labels, y_pred. Accuracy is calculated by accuracy score, counting the proportion of correct predictions over total predictions. Precision, obtained via precision score, measures the ratio of correctly predicted positive observations to the total predicted positives, avoiding false positives. Recall, calculated by recall score, quantifies the correctly identified positives from all actual positives, highlighting false negatives. Lastly, the F1 score is found using F1 score, combining precision and recall into a single metric that balances both, useful when seeking a balance between identifying relevant instances and avoiding over-penalizing either false positives or false negatives. Grid search. Grid search is a technique used to find the best combination of hyperparameters for a given model. This method exhaustively searches through a specified subset of hyperparameters, evaluating each combination using cross-validation to determine which hyperparameters yield the best model performance. In this code, we instantiate grid search CV with an SVM classifier, SVC. Param grid defines the grid of parameters we want to search over, with different values for C, penalty parameter of the error term, gamma, kernel coefficient, and the kernel type. The grid search CV object then performs an exhaustive search over the specified parameter values for the SVM. Refit true means that once the best parameters are found, the model is retrained on the whole training set using these parameters. The verbose2 argument provides detailed logging information during the search. After defining the grid and the search criteria, .fit xtrain, ytrain trains the grid search on the training dataset to find the best hyperparameters. Random search. Random search is a technique used for hyperparameter optimization in machine learning models. It randomly selects combinations of parameters to train the model, unlike grid search, which systematically tries every combination. This approach can be more efficient for searching large hyperparameter spaces or when we have limited computational resources. In this code, we're using randomized search CV from scikit-learn to implement random search on a random forest classifier for classification problems. The param-dist dictionary defines the space of hyperparameters we wish to explore, including choices for max depth, max features, and others. We configure randomized search CV with n_iter equals 100 to limit the search to 100 iterations, and CV equals 5, indicating 5-fold cross-validation. Verbose equals 1 enables verbose output, random state equals 42 ensures reproducibility, and njobs equal -1 allows the use of all CPU cores for parallel computation. Random search.fit_y initiates the search across the defined space on the dataset xy. Bayesian optimization. Bayesian optimization is a strategy for finding the minimum of a function that is expensive to evaluate. It's highly beneficial for hyperparameter tuning in machine learning models, where each evaluation can be time-consuming. Bayesian optimization builds a probabilistic model of the function and uses it to select the most promising hyperparameters to evaluate in the true function. This code demonstrates the application of Bayesian optimization for hyperparameter tuning using Bayes Search CV from the scopt library. It starts by importing necessary components and loading the dataset. Bayes Search CV is initialized with an instance of SVC support vector classifier and a search space for C and gamma parameters, where both are set to vary over a log uniform distribution. The number of iterations, n-iter, is set to 32, indicating that 32 different combinations of C and gamma will be evaluated. The model trains on the dataset and then reports the best hyperparameter values found. This approach systematically explores the hyperparameter space while efficiently narrowing down to the optimal values. Natural language processing, NLP. Natural language processing, or NLP, allows computers to understand, interpret, and manipulate human language. NLP combines computational linguistics with machine learning and deep learning models. A fundamental task in NLP is sentence tokenization, which involves breaking down text into its constituent sentences or words. This process is foundational for tasks like sentiment analysis, machine translation, or information retrieval. In this code snippet, we first import the NLTK library, a popular Python library for NLP tasks. We ensure to download the punct package, which is a pre-trained model for tokenizing English text. The sent_tokenize function is then used to split the provided text into sentences. The output will be a list where each element is a sentence from the original text. This process of sentence tokenization is a critical first step in many NLP pipelines, setting the groundwork for deeper analysis or transformation. Computer vision. Computer vision is a field of machine learning that enables computers to interpret and understand the visual world. By using digital images from cameras and videos, algorithms can detect, classify, and track objects or events. A common introductory task in computer vision is image classification. This code snippet illustrates the creation of a simple convolutional neural network (CNN) model for image classification using Keras, a popular deep learning library. The model starts with a convolutional layer, conv2D, that applies 32 filters to the input images to capture spatial hierarchy. Following this, a max pooling layer, max pooling 2D, reduces the spatial dimensions of the output from conv2D to reduce computational complexity. The flatten layer converts the 2D arrays from the pooled feature maps into a 1D array. Finally, two dense layers, also known as fully connected layers, are applied. The first dense layer with 64 neurons and ReLU activation function to learn the nonlinear relationships, and the second dense layer with 10 neurons and a softmax activation function to classify the images into one of the 10 classes. Speech recognition. Speech recognition is the ability of a machine to understand and process human speech. A simple example of speech recognition is converting spoken words into text. We'll be using Python's speech recognition library as it provides an easy way to convert speech into text. This code snippet demonstrates basic speech recognition in Python using the speech recognition library. We first import the library and create a recognizer object. Using the recognizer, we capture audio through the microphone with sr.microphone. The listen method listens to the audio source and stores it in audio text. Finally, recognize Google method is used to convert the speech into text using Google's speech recognition API. If the speech is understood, it prints the converted text. Otherwise, it handles the error gracefully by printing an apology message. This example highlights the simplicity of integrating speech recognition into applications. Time series analysis. Time series analysis involves understanding trends, patterns, and seasonal variations in timestamp data. It's crucial for forecasting in various domains, such as finance, weather, and sales prediction. Here, we'll focus on a basic example, decomposing a time series into its components using Python's statsmodels library. This code snippet demonstrates loading the statsmodels library to decompose a time series dataset. We first generate a sample dataset with dates and corresponding values, imitating a time series. This data is put into a pandas data frame, with dates set as the index, making it easy for time series manipulation. The key function here seasonal decompose, then decomposes the time series into three elements: trend, seasonality, and residue. The model parameter specifies the nature of the decomposition, which can be additive or multiplicative, depending on whether the components add up or multiply to form the original series. The decomposition allows us to analyze and understand the underlying patterns in the series more clearly. Recommendation systems. Recommendation systems are algorithms aimed at suggesting relevant items to users. Key techniques include collaborative filtering, content-based filtering, and hybrid methods. Here we'll focus on a simple collaborative filtering example, where we predict the rating a user might give to an item based on ratings from similar users. The code demonstrates a basic implementation of collaborative filtering using the SVD, singular value decomposition, algorithm with the surprise library. First, the Movie Lens 100K dataset is loaded, which contains 100,000 movie ratings from users. A reader object is defined to parse the data. Then, the SVD algorithm, which is a matrix factorization technique to discover latent features underlying the interactions between users and items, is applied. Finally, cross-validation is performed to evaluate the algorithm's performance in terms of root mean square error, RMSE, and mean absolute error, MAE, providing insights into the effectiveness of the recommendation system. Problem definition. At the core of any machine learning project is a clear understanding of the problem you're aiming to solve. This step involves thoroughly defining what the business or research question is, what the desired outcomes are, and the scope of the project. It sets the stage for identifying the data you need, the type of machine learning model to use, and how success will be measured. The code snippet represents a concise way of defining a machine learning problem. It encapsulates the primary goal, objective, how success will be measured, success metric, the data to be used, scope, and any known constraints or limitations. This structured approach ensures clarity and alignment among project stakeholders, guiding future steps such as data collection, model selection, and evaluation. Data collection and cleaning. Before we can train any machine learning model, we need to collect and clean our data. This process involves sourcing the data from various locations, understanding its structure, and then cleaning it to make it usable for modeling. Cleaning might involve removing duplicates, handling missing values, or converting data to a suitable format. In the code snippet, we're using the pandas library to perform basic data cleaning tasks on a dataset loaded from a CSV file. The drop duplicates function removes any duplicate rows, ensuring each data point is unique. Then, fillna fills any missing values with the mean of their respective columns. This approach provides a basic foundation for preparing data, making it suitable for further analysis or model training. Feature engineering. Feature engineering is a crucial step in the machine learning project lifecycle, where raw data is transformed into features that better represent the underlying problem to predictive models, resulting in improved model accuracy on unseen data. This step can involve several tasks, including encoding categorical variables, handling missing values, and creating new features through domain knowledge. This code snippet demonstrates one of the basic processes in feature engineering, encoding categorical variables. We start by importing pandas, a popular data manipulation library. The sample data consists of an age column and a gender column, where gender is a categorical variable. Using pandas' getDummies function, we encode the gender column into numerical format. This transforms the gender column into two columns, gender female and gender male, with binary values, 0 or 1, indicating the presence of each category. Encoding categorical variables in such a way is essential for most machine learning models because they require numerical input. Model selection. In the model selection phase, we compare different machine learning algorithms on a given dataset to choose the one that performs best according to a specified metric. This phase involves training several models using the same training data and then evaluating their performance on a validation set. We'll use Python's scikit-learn library to demonstrate selecting between different models. In this code snippet, we start by importing necessary modules and functions from scikit-learn. We load the iris dataset, split it into training and test sets using train, test, split, and define our models, logistic regression and random forest classifier. Both models are trained on the training set. Post-training, predictions are made on the test set, and the accuracy of each model is calculated using accuracy score from the test set predictions. Lastly, we print the accuracies to compare the performance of the two models. This process aids in model selection by allowing us to determine which model performs better for our dataset. Training and testing the model. Training and testing a model are crucial steps in a machine learning project. Firstly, you split your dataset into two parts, one for training the model and the other for testing its performance. This helps in evaluating how well your model generalizes to new, unseen data. Let's consider a simple example using a dataset split and linear regression model from the scikit-learn library. In this example, we start by loading a dataset using the load Boston function, which gives us Boston housing price data. We split this dataset into training data, xtrain, ytrain, and testing data, xtest, ytest, using train test split, reserving 20% of the data for testing. A linear regression model is created and trained using the training data with the fit method. Finally, the trained model is used to make predictions on the test set with the predict method. The predictions can then be compared to the actual test labels, ytest, to evaluate the model's performance. Deployment. Deployment in machine learning is the phase where the model is integrated into an existing production environment to make predictions based on new data. This can involve activities such as converting the model into an appropriate format for the target environment, setting up a serving infrastructure, and implementing continuous monitoring. Below is a simplified example of deploying a machine learning model as a Flask web service. This code snippet demonstrates deploying a machine learning model using Flask, a lightweight web framework. First, the Flask library and joblib for loading the model are imported. An instance of the Flask application is created, and the trained model is loaded from a model.joblib file. A /predict endpoint is set up to accept post requests, where JSON data can be sent to the server. The model uses this data, features, to make a prediction, which is then returned as a JSON response. This setup is a basic example of how a machine learning model can be made accessible over the web, allowing other services or applications to use the model's predictions. Monitoring and maintenance. After deploying a machine learning model into production, the next crucial phase is monitoring and maintenance. This phase ensures the model remains effective over time and adapts to new data or trends. We'll look into a simplified model monitoring using Python. In this code, a mock function, monitor model performance, is defined to simulate the monitoring phase by evaluating the model's accuracy. The accuracy score function from sklearn.metrics is used to compare the true labels against the predicted labels to calculate accuracy. This simplistic approach shows how to periodically check a model's performance. It's crucial in real-world scenarios to expand on this by incorporating more complex metrics and possibly automate the monitoring process to address issues such as data drift, model decay, or changing environments automatically.